Now, what about the cutting tool used in this operation? Here's the cutting action in slow motion. It's slowed down nearly 200 times. As in most drills, there are two cutting edges. As it rotates, it's fed into the work and generates a hole. Now, the cutting edges of the twist drill have rake and clearance angles similar to those of a planer tool. Let's look at a diagram and compare the two. Here's the twist drill, and here's the planer tool. Both have a similar wedge-shaped cutting edge. Here's the clearance angle for the planer tool. It's the same for the twist drill. And here's the rake angle of the planer tool. For the drill, this angle is called the helix angle. The helix angle is the rake angle at the outside edge of the drill. Now, in order to cut a wide variety of materials, drills are made with different helix angles. These three here are all different. The one on the left has a large helix angle. The one in the middle, a small helix angle. And this one here, no helix angle at all. This drill can be used for cutting a material such as brass. Can you find out what materials you'd use the other drills for? In order to cut efficiently, the cutting edges of all tools like this twist drill must be properly ground. The geometry of a twist drill is such that it needs to be sharpened on a suitably designed machine. Let's take a closer look at the geometry of a drill point. First, the end of the drill. It has two cutting edges, one here and the other here. If we look at this drill from the side, you can see that these cutting edges are arranged at an angle to each other. Let's put this information in a diagram. Now, the angle at which the two cutting edges are arranged is called the point angle. For most standard drills, this is about 118 degrees. If the drill is ground correctly, the point of the drill will be on center, and the length of each cutting edge or lip exactly the same. We call this length the lip length. As the cutting edges are at an angle to each other, one end is higher than the other. This difference in height must be the same on both sides. It's called the lip height. Now, this is for a drill that's been correctly point ground. Here's a drill that's been incorrectly ground. This cutting edge, or lip, is longer than this one. And the lip height this side is greater than the lip height this side. But the point of the drill is still on center. What effect do you think this will have on the cutting action of the drill? To find out, we set up the drill in a special drilling machine, a radial drill. It's difficult to see what's happening here, so we'll take a closer look at part of the cutting action in slow motion. This is nearly 200 times slower than it actually happened. Can you see what's happening? Only one cutting edge appears to be cutting. Although there's some swarf in the other flute of the drill, it's not flowing, so it can't be cutting on that side. The cutting edge or lip that's doing all the work is the one with the shortest length. Because the drill is only cutting on one side, the cutting force is uneven. All the force is on one edge only. If we now look at the cross-section of a hole produced by this drill, we can see why this happened. See how the shorter lip took the cut. The longer lip followed round with nothing to do. Here's another drill that's been incorrectly point ground. Again, one lip is longer than the other. But in this case, the lip heights are both the same. Well, almost. And this time, the point is off-centre. Let's see what effect this will have on the cutting action of the drill. Did you see how the point described a circle as it entered the work? Here's part of that cutting action in slow motion. Again, only one cutting edge appears to be cutting. This time, it's the longer one of the two. There's some swarf from the other cutting edge, but it's not flowing, so no cutting is occurring on that side. With material being removed on one side only, the cutting forces on the drill are again unbalanced. How has this affected the accuracy of the hole? It's oversize, and the point continued describing a circle as the drill cut down into the work. Another drill, another example of bad grinding. Here the cutting edges have different lengths, the lip heights are different, and the points off-centre. Can you work out what effect this will have on the cutting action? As with the drill, so with any tool. The right grinder must be used to get correct geometry. A milling cutter like this is normally sharpened on a cutter grinder, but it's a highly skilled job and should be left to those who know how to do it. When it comes to sharpening lathe tools, it's usually possible to use a relatively simple grinding machine, like this one. It has a table which can be set to almost any required angle. Once the angle is set, the table must be moved in towards the grind wheel. Can you think why? The wheel is checked to ensure it's free to run, and the machine is now ready. Here, we're grinding the clearance angle on a knife cutting tool. How would you grind the rake angle?